So in this video we're going to define the triple scalar product and then show why the absolute value of it gives you the volume of the parallelepiped. So triple scalar product is simply if we have three vectors in 3 space, if we u, v, and w, if we take u dot v cross w, this by definition is the triple scalar product of u, v, and w. So we're just giving this product a name. And notice this is going to be a scalar because when we take v cross w, which is in parentheses, so we do this first, the result is a vector, and then we're doing the dot product of a vector with another vector, and the dot product always generates a scalar result. So you expect to get just a number out of it. And the claim is that, the claim is that you can calculate the triple scalar product just by taking this determinant where you take u, the component form of u, v, and w, and you put the component form of u in as the first row vector, you put v in as the second row vector, and w in as the third row vector, and you calculate this determinant. And you get to do that in the homework. So in the homework you're going to be asked to verify that this calculation can be done using this determinant. And then in the homework you're going to be asked to calculate volumes of parallelepipeds. And the idea is, or the claim is, that if you want to find the volume of a parallelepiped, you just need to take the absolute value of the triple scalar product, which you can calculate by taking the absolute value of this determinant that you're going to demonstrate in the homework is a way to calculate the triple scalar product. And the proof that the triple scalar product, the absolute value of it, gives you the volume of a parallelepiped is pretty straightforward. In a parallelepiped, all we do to make a parallelepiped in 3 spaces, we take we want non-parallel vectors. So we take a vector u, so we'll call this guy u. We take a vector w, should draw them on the line. We take a vector w, like this, and then we take a vector v, and then the parallelepiped is constructed from the parallelograms that those 3 vectors form in 3-dimensional space. And the idea is that the volume of a parallelepiped, you calculate it by finding the area of the base of the parallelepiped. That base is repeated all the way up to the top, and then you multiply by the height of the parallelepiped. So there's a sense in which you're just counting how many times the area of the base repeatedly occurs. So here's the idea. We know if this is w and v, we know if we take the cross product, and let's give it a name, if r is the cross product of w and v, we know that the cross product, or r, is perpendicular to both w and v. So right here, if I put the cross product of w and v right here, it would be perpendicular to both of them. And then I could establish a line that contained that vector w cross v. And if I drop a perpendicular from the terminal point of vector u to that line, the distance that I get right here is the height of the parallelepiped. But if I think about the vector from here to here, that's just the projection of u onto that cross product. So the vector from here all the way to here, we've already shown that this is the projection of u onto that vector, and I named that vector r. He's the cross product. So to get the height of this parallelepiped, I just need to take the size of that vector. And then the base of a parallelepiped is just a parallelogram formed by vectors w and v. And we showed in the previous two videos ago, we showed that the area of that parallelogram can be found by just taking the size of the cross product of w and v. So ultimately, because the volume of a parallelepiped is found by taking its height times the area of the base, we can replace the height with the size of the projection of u onto the cross product. That will give us the height over here. and then the area of the base can be replaced with the size of the cross product down here. It doesn't matter if we do W cross V or V cross W. Remember that we just get the opposite vector, but we're taking the size, so the size will be the same regardless of the direction in which we take this cross product. And then what we want to remember is, how did we define the projection? Well, projection was defined to be, if we were projecting a vector u onto a vector v, the size of that, we'll say we're projecting onto r in this case. So the way that we got the projection vector was we took u dot whatever we were projecting onto, and then we divided by the size of the vector we're projecting onto squared, and then to get the vector we multiply again by the vector r. And then the trick that we played in previous videos is we took this squaring and we put one of them under the vector r, so that r divided by the size of r is a unit vector, which then identified to us that this scalar right here is the size of the vector. So the absolute value of that scalar is going to be the size of the vector. So to find the size of the projection, we just replace it with u dotted with our vector r divided by the size of the vector r. So we're replacing the size of the projection with this right here, the scalar that multiplies the unit vector. And once we do that, we can see that we get the size of the cross product of u and v showing up twice. So it's going to cancel and give us a 1. And because this is the size, or absolute value, we're going to get the absolute value of u dot v cross w. And if you demonstrate in the homework or prove that this is the same as this tells you that when you're doing your parallelepiped volume calculations in the homework, you can just take the absolute value of this determinant to get the volume that you need. So the trick in the homework is going to be, if you're given points and you're told that those points form a parallelepiped, use those points to find the vectors u, w, and v by doing the appropriate subtractions. Terminal point minus initial point, terminal minus initial, terminal minus initial. Get your vectors and calculate a determinant. I'm not going to show an example because I think the calculation is pretty straightforward.